directional derivatives. So if you remember, we had partial derivative of f with respect to x, where we had, z equals a function of two variables, x and y. So this is the derivative in the direction of the x-axis, and the partial derivative of f with respect to y is the derivative in the direction of the y-axis. And so, of course, we had other notations: partial of f with respect to x, partial of f with respect to y. So what we're going to do now in this section, what's different about this is we're going to have a curve or a sheet or a cylinder, and then we're going to take any direction. So we're just going to go instead of being in the x direction, which actually comes out of the screen, right? In the x direction or the y direction, we're gonna take see what the derivative is in any direction, and we're gonna let a unit vector in that direction kind of dictate what's going on. And what we're gonna do is that unit vector. So I'm gonna draw the x and y axis like we normally look at it in 2 dimensions. So if I've got the x-axis here and the y-axis here, then if I've got a unit vector here in this direction, basically what I'm going to do is I'm going to let theta be the angle from the positive x-axis. So we can if we have a height z for our point, so like down here we got some piece of 0, which that point that we start from is x0, y0, z0. But what we can do is we can drop that down, so to speak, and just look at that in this axis, so that it'd be x0, y0, and then 0. So anyway, so that's kind of what we're doing, and so we have a surface that we want to. So if I have a surface, with a point on it here, and I want to look at the derivative in this direction, that'd be a directional derivative. And so what we can do once again is drop that down. If this is the z-axis, I can drop that down, that point down here, and put it in the xy plane, and check out a derivative from that. So anyway, we'll get going on that. I think the actual results and theorems are pretty easy on this, and so you do have some notes on this as well, which is nice. So this is section 12.6, and anyway, we're gonna define what a directional derivative is. So let f be a function of 2 variables, x and y. Okay, let that be defined. So basically I just said let f be a function defined in terms of x and y, and we're going to let u be a directional vector, u vector. So it's u vector. It's going to be given by cosine theta I plus sine theta j. Okay, and so basically it looks like that picture. So that is a unit vector in a particular direction. Once again, theta is a positive angle with the x-axis. Okay, and then the directional derivative of f in the direction of u vector. So it's of f of xy in the direction of u vector. The direction of u vector is going to be denoted d sub u. So like we had d sub x direction or the derivative, partial derivative in the direction of the x-axis. Now we're going to have the derivative of f in the direction of u vector. So we're going to have this. Now they do have a definition of this, and basically they say that the directional derivative of u of f, in the u vector direction is going to be the limit as h approaches 0 of f of, in this case, we're going to say x plus h cosine theta. So we're gonna move that angle just a little bit. So if u vector is right here, what we're gonna do is we're gonna move that a little bit more. So anyway, f of x plus h cosine theta, y plus h sine theta, and then minus f of xy all over h. So that's the formal definition of a directional derivative, a derivative in the direction of u vector here. So anyway, with this is just a little tiny change there, etc. And that's a minus f of xy there. So we're not going to really use this. You don't have to use that in your exercises. It's not hard to do. They have a nice example in the book there. But we do have a nice theorem that we get from this. And so one of the theorems is that if we want the directional derivative of f in the direction of u vector, then what that ends up being is the partial derivative of f with respect to x times cosine theta plus the partial derivative of f with respect to y sine theta. So we have a very nice formula that we get that we can use this to come up with stuff. So anyway, let me see if I want to cover gradient first or something else. Let's see. So that's the dim lighting here, so I gotta get my flashlight out and stuff too. But anyway, so let's look at an example. If I've got f of xy, this is in your notes as well, but anyway, I'll just kind of talk you through it. F of xy is 2x squared plus 5y squared, and we're going to let u vector, so the direction I want is pi over 4 from the x-axis. Okay, so it's going to be, this is given, we choose this, so this is the direction I want to look at, so it's 45 degrees positively from the x-axis. So it's cosine pi over 4i plus sine pi over 4j. Okay, so basically I've got my curve here, which is probably a paraboloid or something of that nature, but anyway, so then we're going to look at this at, we could really look at any particular point, right, to start with, but right now I'm going to do it in general. The directional derivative of f in the direction of u vector given here is just going to be, once again, the partial of f with respect to x. So here's my function. So the partial of this with respect to x is going to be 4x, right? And then the 5y squared is a constant, and then times cosine theta. Well, cosine theta is cosine of pi over 4, which is square root of 2 over 2, right? So we have that, and then plus the partial of f with respect to y. So once again, the first 2x squared would be considered a constant, so that'd be 10y to the first, and then times the sine of pi over 4, because that's my angle here, is going to be square root of 2 over 2. And then, of course, we're going to simplify that, and we know that 4 cancels with 2, and I get 2, and 10 cancels with 2, and I get 5. So this is equivalent to 2 root 2x plus 5 root 2y, and that would be the directional derivative. Now, what we could do is we could actually look at a particular point too. So if I want the directional derivative of f in the direction of u vector, where this is my u vector pi over 4 angle from a particular point, if I want a particular point, so this is not in your notes, but if I have a particular point and let's just use the point 1, 2, okay, for the x0, y0. What I could do then is I could then just plug them in right here to figure out the directional derivative of f evaluated at 1, 2 is going to equal, in the direction of u vector. Once again, u vector is the same pi/4 angle from that point on the curve, but once again, instead of being up at z, we can drop it down to the xy axis, let z be 0, and then look at what the derivative looks like. So there's some nice pictures of that in the book. But anyway, so we would just plug that in, and we're going to get, sorry, that wasn't parentheses, that was circle there. So it's going to be 2 root 2 times 1, which is 2 root 2, plus 5 root 2 times 2, so 10 root 2, or simplifying that, it's 12 root 2. Okay, so the directional derivative of f evaluated at 1, 2 in the direction of u vector, which is a pi/4 angle, is 12 square root of 2. Okay, notice that, so if u vector, and just kind of show you, if u vector is cosine theta I plus sine theta j, and that's going to be the general u vector. I'm just going to let you kind of realize the if we want to go in the direction of the x-axis, what do we know? So theta would be 0, right? So theta equals 0. We would, because theta is the angle from the x-axis in the positive direction. So in this case, theta would be 0. So what would u vector be? U vector would be cosine 0 I plus sine 0 j. Well, this sine 0 is 0, right? So with that being said, we've got cosine theta. Cosine of 0 is 1. So this ends up being I, right? So the unit vector is I, so in the direction of x. And anyway, so that's going to lead to, if theta is 0, that's going to lead to just, that becomes the partial derivative of f with respect to x. So it's the directional derivative in the I direction is the partial derivative of f with respect to x. Similarly, if we want to go along the y-axis, that would mean that theta equals pi/2, right? So if theta equals pi/2, then we have u vector is going to be cosine of pi/2, which is 0 I, plus sine of pi/2 is 1 j, so that's equivalent to j hat, right? So basically, this is going to lead to the partial derivative of f in the y direction, the directional derivative in the y direction is the same as the partial derivative of f with respect to y. And then we're going to get into gradients here as well. And so I do need to look at what a gradient is. Okay, so so here's a definition. First of all, we're going to let f in terms of x and y exist. Okay, so we get outputs there. We're also going to let the partial derivative of f with respect to x and the partial derivative of f with respect to y, we want these all to exist. Okay, so if these all exist, then we're going to be able to come up with what a gradient is. So the gradient of f denoted, it's denoted like this. It's an upside down delta. It's actually a bold delta, which I don't have that font, so I just put a, sometimes the book says that you can call that del instead of delta. I call it grad because it represents a gradient, so I'm just using that. So it's grad f, so it's an upside down bold delta. We'll just use an upside down delta. Is given by this. It's a vector. So that's the grad f is a vector. Okay, so we want that. and grad f is given by the partial of f with respect to x evaluated at xy in the I direction plus the partial derivative of f with respect to y evaluated at xy in the j direction. Now, just for short, what I'm going to do is I'm going to shorthand this. Mathematicians don't like writing all that out, right? Like, you know, we didn't really need to put evaluated at xy, right? We could be xyz, etc. But anyway, so I'm just going to shorthand this and say, hey, this is a vector notation, so it's the vector partial of f with respect to x, partial of f with respect to y. So that's the gradient of f when we have a function xy. Similarly, we could have, you know, if we have f of xyz, right? So w equals that, and then we would have to have fx, partial of f with respect to x, partial of f with respect to y, partial of f with respect to z all exist. Similarly, what would the gradient of f be? It would be given by the vector partial of f with respect to x for the first component, partial of f with respect to y, for the second component, partial of f with respect to z for the third component. So we could very similarly do that as well. So it is a vector. What's nice about a gradient is it has a very easy application into the directional derivatives. So what was the directional derivative of f in the direction of u vector? If you remember, it was cosine theta, what was it? I got to remember what it was. It was partial of f with respect to x cosine theta plus partial of f with respect to y sine theta. But if we wanted to, we could remember what a dot product is. We set stuff on top of each other and multiply. We could say, hey, this is basically cosine theta I sine theta j plus sine theta j, sorry. But I'm going to write it as vector notation, and then dot partial of f with respect to xi plus partial of f with respect to yj. Once again, written as vector notation here. I could write it like this instead of using the i's and j's. You could use i's and j's. We would just have parentheses instead of this vector bracketology here. But anyway, if you take the dot product of these two things, remember you put them on top of each other, multiply and add them together. That's what these things are. Of course, we know that the first one is nothing more than u vector, right? So that's u vector right here. And then dot, and then what's this? This is the gradient of f. So this is a very nice formula here that the directional derivative of f in the direction of u vector is just simply given by the dot product of u vector dot the grad of f. So very nice result here. So this is one that, you know, we're definitely going to want to use, etc. So I believe I'm now flipped over to page 33 on your notes, and we're gonna use this. I just got a particular example here. We'll step through, and anyway, so g of xy we're saying is the natural log of the square root of x squared plus y squared. Okay, and then so we want to find out what's grad of g? Well, that's grad of g is the partial of g, not f, so the notes are actually wrong here. So the partial of g with respect to x, I hat plus partial of g with respect to y, j hat, right? Or basically we could have just wrote that like this, right? Anyway, so what we can do is we'll go with this because that's kind of how I did it in my notes. But anyway, partial of g with respect to x. Well, I need to rewrite this a little bit, so I'm going to write that as natural log of x squared plus y squared to the 1/2 power. Of course, we can take that 1/2, drop it down in front, right? and then that makes it a little bit better. So now it's 1/2 natural log of some function. So the partial of this with respect to g, it's 1/2. Remember, the derivative of natural log is 1 over, natural log of x is 1 over x. So this is going to be 1/2 times 1 over that thing, which is x squared plus y squared, times the derivative of what's inside by the chain rule, right? So derivative of what's inside, but it's a partial of g with respect to x. So that just, the partial with respect to x here is 2x, and then the y squared is a constant. So that goes away. So this is your I term here, plus the j term is going to be a similar deal where we take the derivative of this with respect to y. It's going to be 1/2 times 1 over x squared plus y squared. And of course, derivative of what's inside in this case, it is y squared, so it's a 2y, and then j hat, right? So then we can kind of clean this up a little bit. We notice that the 2's cancel out, makes that a little nicer, and we get that this is equivalent to x over x squared plus y squared I hat plus y over, sorry, I forgot my squared, plus y over x squared plus y squared j hat, right? Or if we wanted to just write it in vector notation, it's x over x squared plus y squared and y over x squared plus y squared with a comma in between, write it in the vector bracket notation. Okay. Anyway, the other thing we could do, which I did in the notes there, is if you got the same thing multiplied, I could factor out. So I could factor out the 1 over x squared plus y squared, and I could write it as 1 over x squared plus y squared times, so scalar multiplication there, times the vector xy. Okay, so that is an alternate correct form of an answer. So any of these are correct representations of what the gradient of g is. And like I said, just adjust your notes. So grad g is not f sub x, it's g sub x I plus g sub yj. Okay, and then the next one, we're looking at an example where it says, hey, find the directional derivative of f in the direction of u vector at a particular point for a particular angle. And so in this case, we're looking at example 15, and this is find, so our particular point is 1, 2, okay? And then we have f of xy is defined by x squared minus 2x y squared, so pretty easy one there. And then the u vector that I want to take the directional derivative in this direction is going to be cosine pi, so cosine pi I plus cosine pi, sine pi j. Okay, so basically I'm going pi units from that. So let's just say, I'm not sure what this is, but you know, if we got our sheet here and we got a particular point, we don't care what z is, so we can drop that down. So basically, I've got a directional derivative going in the pi direction from the x-axis. So if x is out to the right here, pi units from that point is coming over this way, going the opposite way. So once again, there's some nice pictures in the book that I can't do, trying to hurry on a slippery surface here. But anyway, of course, we know what cosine pi is. Cosine pi is -1. Sine of pi is the height at 0. So this ends up being -1, 0, right? Or negative I plus 0j, or just minus I, right? If you wanted to write it that way. But I'm going to leave it in vector notation because I'm going to use gradient, the dot product here. And so the directional derivative of f in the direction of u vector, which is pi units from the x direction, x-axis, positive x-axis, is going to be given by u vector dot grad f. Okay, so what's grad f? It's going to be grad f. Let me write this out first. So it's u vector dot grad f, and then what's that equivalent to? That's going to be u vector dot grad f is partial of f with respect to x, partial of f with respect to y vector. So anyway, so this ends up being -1, 0 dot that vector, directional, or the u vector is -1, 0, and then dot with the vector partial of f with respect to x. Let's go back up here. So I've got 2x, and then x is my variable here. So I got 2y squared, so minus 2y squared. And then I've got, do it in terms of partial in terms of y. The first one's a constant. And then, so anyway, bring that 2 down, and I'm going to get minus 4 x would be the constant part, y to the first. So I believe that's what I should get there. And then if I take this dot product for the directional derivative of f in the direction of u vector, I will just get minus 1 times this one, basically is opposite sign. So I'm going to write that as 2y squared minus 2x, and then plus 0, right? So this is what I end up getting there. And then if I want to figure that out, plugging in, I'm not sure, she wrote -2 in the notes there, but I have 1, 2 here. So if I want to figure out what that is up here, I'm going to plug in my point right down there, and I'm going to get the directional derivative of f in the direction of u vector at the point 1, 2. When I plug that in, I'm going to get, plugging in x is 1, so that's -2, y is 2, so 2 times 2 squared is 8. So this ends up being 8 minus 2, which is 6. So I think that was just a typo. She didn't have a -2 there, so we'll have to fix that. But anyway, that's the directional derivative, and we'll go from there. So